morning, students. Myself, Vijay Shankar from EC Department, Shipbuil Engineering College. So today we are going to discuss about another topic in the magnetostatics, H bar due to the circular loop. In the last class, we discussed about the H bar due to the infinite straight conductor and H bar due to the finite straight conductor. Now, in this class, we can discuss about the H bar due to a circular loop. Circular loop. H bar on the axis of a circular loop. So consider a circular loop carrying a direct current I. It's a circular loop here. It's a conductor carrying a direct current I, placed in XY plane with the Z axis as its axis as shown in the figure. Z is an axis in the center here. This plane is XY plane. This is XY plane, my dear students. The circular loop is placed on the XY plane with the axis as a Z axis. The magnetic field intensity H bar at point P is to be obtained on the Z axis here. The point P is at a distance of Z from the plane of a circular loop. The point P here, the distance is Z and it is towards the AZ bar. And a small differential length is assumed on the circular loop with I into dl bar. From this point to the origin, the distance is r and it is towards the negative direction of r, so minus a r bar r into the two components we got to find out the r12 bar, because it's a point 1 to the point 2 we are finding. Okay, the radius of the circular loop is r. Circular loop is r, so distance between the differential length dl bar and the 0 is also the r. Consider a differential length dl bar of a circular loop as shown in the figure. In the cylindrical coordinate system, dl bar is equal to dr into ar bar, r into d phi a phi bar, and dz into az bar. You know this one. From the coordinate system, the differential length of the cylindrical coordinate system is dl bar is equal to dr into ar bar plus r into d phi a phi bar and dz into az bar. Okay, my dear students. Now, I into dl bar, but the dl bar is in the plane for which r is a constant and z is equal to 0. It's a constant plane. The ideal bar is a tangential at a point 1 in the a phi direction. So ideal bar is equal to I into r d phi a phi bar, r d phi a phi bar, because it is a circular loop. It is a tangential to the point 1 in the a phi direction. A phi direction. See here, this is a phi is there. The point P is a I into dl bar. So ideal bar is equal to I into, we are not taking the r component and the z component. We are taking only the phi component, r into d phi a phi bar. Ideal bar is equal. And the base vector ar bar or ar12 bar is equal to 1 to the base of point, 1 to the point. Here the vector of r bar and the magnitude of that vector, and r12 bar having the two components. One is z into az bar, is a plus minus students. Plus z az bar minus r into ar bar. So r bar is equal to having the two components. Plus z az bar is a positive z direction upwards, and actually the r is towards this direction is a plus ar bar, and the direction is opposite to the plus ar bar is a minus r into ar. Minus r into ar bar. Okay, and its magnitude is the square root of r square plus z square. A r12 bar is equal to, so vector minus r bar and plus Z AZ bar under root of R square plus Z square. We need to apply the cross product of DL bar cross AR12 bar is equal. First of all, it is a cylindrical coordinate system is AR, A5, AZ. DL bar coefficients. What is a DL bar coefficient? Here it is a D5, A5 is there, IR D5. I'm not taking the I here, only the DL, so R into D5. Okay. There is no any R term and there is no any Z term, only the phi term is there, that is R into D5. And what about the AR bar? For our convenience, denominator can keep not taking now. In the simplification, and AR and AZ, R is a minus R, and phi is a 0, and Z is a Z coefficient. Let us take it as a R. AR is a 0 into 0, R into Z D5. When I am taking this AR bar into R D5 into Z. Okay. A5, you can see here the 0 and here also the 0, both are the 0, they are not getting A5 plus Z. So 0 into 0 minus of minus. So AZ bar into R into R D5. R into R D5. So finally this becomes of Z R D5 A5 bar plus R square D5 AR AZ bar. Is an AZ bar. Okay. Now substitute this equation in the H bar equation or the differential H bar. DH bar is equal to IDL bar cross AR bar, IDL bar cross AR bar by 4 pi R square. Okay. In this DL bar cross AR bar, what is a Z into R D5 A5 bar or the A5 AR bar and R square D5 AZ bar. In the denominator, the 4 pi R square. R square means under root of R square plus Z square whole square is R square. And under root of R square plus Z square is A bar. Okay. Now the both of simplifying the function, the DH bar is equal to I'm multiplying the I and write the DL bar cross AR bar I into the ZR D5 A5 bar plus R square D5 AZ bar whole divided by, in this only it is a denominator is there, R square plus Z square, and the distance, the square of the distance is R square plus Z square under root whole square into 4 pi. So simplify the denominator I into ZR D5 A5 bar plus R square D5 AZ bar whole divided by the 4 pi into R square plus Z square whole power 3 pi. Here it is a 1 by 2 and this one is a square and this root is get cancelled. 1 plus 1 by 2, 3 by 2 will get. But it might as well. Then, see in this term, I into ZR d phi, and the d phi is a common term here. Then take the d phi integral with respect to phi is varies from 0 to 2 pi. Phi is varies from the 0 to 2 pi, and the theta is varies from the 0 to pi on. And I into ZR AR bar plus R square AZ bar d phi, and the 4 pi R square plus Z square whole power 3 pi. Got it? In this, the first integral having the ZR d phi and denominator is same, and R square AZ bar denominator is the same, the two functions. And consider the first integral to prove that its value is 0 due to the radial symmetry. So actually, whenever there is an AR bar component is there, AR bar component, it is eliminated. Because the symmetrical is there, the one side we can take the differential element DL bar means, in the other side is also the symmetrical DL bar. There is no any component of AR bar. So let us see here the eliminating of AR bar also. How it is, mathematically it is proved that ZR R square plus Z square whole power 3 by 2 is a common term. Okay, and the d phi AR bar. Now, the AR bar you can write as a cos phi AX bar plus sin phi and the A phi bar. The unit vector AR bar is expressed in the rectangular coordinate system as cos phi AX bar plus sin phi A phi bar. Cos phi with the integral is sin 2 pi and the sin 0, it is a 0. And integral of sin is again the minus cos phi. By substituting the 2 pi and the 0, the values of cos 2 pi is a minus 1 and cos 0 is a 1. So minus 1 plus 0 is a 0. Okay. Either in the electrical field intensity also, we eliminate the circular loop electric field intensity due to the circular ring. In that AR bar is eliminated, and electric field intensity due to the symmetric, the AR bar component is a 0. Only we have AZ bar component of D is the second term. That is I by 4 pi R square d phi by R square plus Z square whole power 3 by 2 into AZ bar. AZ bar component only because the R bar component is a 0. Got it, my students? And this is a AR bar, the unit vector is expressed in the rectangular coordinate system and the cylindrical coordinate system, where is the cos phi into AX bar plus sin phi into AY bar is in the AR bar. Okay. Now, the integral d phi is a phi, and phi is varies with respect to the, not with respect to, the upper limit is 2 pi and the lower limit is 0. IR square 2 pi AZ bar whole divided by 4 pi R square plus Z square whole power 3 by. Therefore, the H bar is equal to IR square by the 2 into R square plus Z square whole power 3 by 2 into AZ bar. The H bar on an axis of a circular loop. Okay, madam. This R is a radius of the circular loop, and the Z is a distance of point P along the x-axis, along the axis. With the point P is shifted to the center of the loop. Suppose here, actually the diagram looks like this. It is a circular loop with a carrying current. So let us take its origin. Z into AZ bar. Point P, where we have to find out the H bar here. A small differential length you can assume on the circular loop. Due to the symmetric, the AR bar component is eliminated. Now the differential length DL bar you can assume is a 0.2 and here the 0.1. And Z is equal to 0. We get the result of time in the earlier section is Z is equal to 0 means the point P is here at the origin. The point P is at the origin means Z is equal to 0. You can keep here the Z is equal to 0. I R square by the 2 into R square whole power 2 R only. And here the R cube and R square get cancelled. A Z bar. I is equal to H bar is equal to I by the 2R into A Z bar. If it is a B bar is equal to I by 2R bar is equal to mu naught into H bar. Weber per meter square. Weber per meter square, and this is ampere per meter. Okay, and this P bar is shifted at Z is equal to 0. At Z is equal to 0. You get I R square by the 2 into R square plus 0. R square whole power 3 by 2 and becomes of R cube. The numerator R square and the denominator R cube get cancelled. We have only the R in the denominator, I by the 2R. Similarly, it is also the H bar is proportional to the 1 by R. Okay, my friend. In electrostatics, the gas law psi is equal to phi, the magnetic is equal to the charge enclosed Q, not the phi minus 1. So charge enclosed inside the Q is equal to, and the integral d bar dot ds. I want the gas law of electric field. Now here, in electrostatics, the gas law is used to find the E bar in case of complex problems. Similarly, in the magnetostatics, the complex problems can be solved by the law called Ampere's circuit law, Ampere's work law. What is that gas law in the electric field intensity? The Q is equal to integral d bar dot ds. As in the similar of the magnetostatics, the Ampere circuit law is I is equal to, because it is a current. The electric field intensity, we use the charges, and in the magnetostatics, the current carrying conductor surrounding there is a magnetic field. So I is equal to H bar dot dl. H bar dot dl. Ampere's circuit law. Ampere's circuit. We go for the proof of Ampere's circuit law. So consider a loop starting straight conductor. Consider not the loop, my dear students. Consider a long straight conductor carrying direct current I placed along the z-axis as shown in the figure. See the z-axis, there is a long straight conductor carrying the current upward direction AZ bar. Consider a circular path of radius R. The circular path of radius R from origin to the radius of that circle is from origin is a radius R. So you have to consider the point P and the y-axis. Consider a closed circular path of radius which encloses the straight conductor carrying direct current I. The point P is perpendicular the distance R from the conductor. This is a conductor, and the point P is perpendicular to the current conductor, carrying current the conductor with the distance of R, perpendicular distance of R from the conductor. Consider a differential length at point P. Here I am assuming a differential length at DL bar, which is in the A5 direction. Actually, X, Y, Z is the rectangular coordinate system. Z is the same in the cylindrical coordinate system. X is a AR direction and Y is a A5 direction. Okay, so which is the A5 direction tangential to the circular path at the point P. So there is a tangential to the circular path A5, to circular E. Wherever you can take that is a tangential to the circular path. Now H bar is equal to, while H bar obtained the point P from the pivot law due to the infinite long conductor, we know that H bar is equal to I by the 2 pi. So using we have the formula is there, H bar dot DL bar is equal to H is I by 2 pi R A5 bar dot DL bar is along the phi direction, means having the component is R into D phi A5 bar only. Okay, DR is along the R direction component, and R into D phi is A5 bar and DZ AZ bar. In the differential length DL bar, so all it is a L2 combination. So DL bar we can assume only the A5 because the H bar is in the A5 direction. We are not taking the DR and DZ. So A5 bar and A5 bar is a 1. I by 2 pi R into R D phi. R get cancelled. I by 2 pi into D phi. Okay, what is the phi value? H bar dot DL bar is equal to, apply the integral on both sides. H bar dot DL bar is equal to, we got I by 2 pi into D phi. Apply the integral on both sides. Integral H bar dot DL bar is equal to integral I by 2 pi into D phi. Okay, my dear students. I by 2 pi is a constant. What is a D phi? Integral D phi is a phi. Phi is varies from the 2 pi to 0. So I by 2 pi and upper limit is a 2 pi, lower limit is a 0. So 2 pi get cancelled. It becomes of I. So H bar dot DL bar is the integral, my students. H bar dot DL bar is equal to I, current carried by the conductor. This proves that the integral of H bar dot DL bar along the closed path gives the direct current enclosed by that closed path. Okay, so H bar dot DL bar integral is equal to I, or I is equal to H bar dot DL bar, amperes circuit law. Okay. Next. In the electrostatics, we derive the expressions of a long straight conductor, not the long straight conductor, H bar due to the infinite line charge. By using the Gauss law and circular loop by using the Gauss law, and the infinite sheet of charge is also by using the Gauss law. And similarly here also the magnetostatics, you can find out the H bar due to the infinite line long straight conductor by using Ampere circuit. By using Ampere circuit, a long straight conductor on the z-axis, and there is a circular loop with the radius of R, and the point P is perpendicular to the top of R, and is in the A5 direction. A small differential length we can assume at the point P. So H bar is equal to always H5 A5 bar. In that electrostatics, we take the D bar is equal to dr into AR bar, or E bar is equal to ER into AR bar. Now here the A5 H5 into A5 bar. DL bar is equal to along the direction of phi R into D5 A5 bar. H bar dot DL bar is equal to H5 R D5. A5 and A5 is a 1. According to the Ampere circuit law, H bar dot DL bar is equal to I. So H bar dot DL bar we got as H5 into R D5 with the limits of 0 to 2 pi with respect to the D5 is here. So H5 and R is a constants. H5 and R with the integral of phi, upper limit is a 2 pi, lower limit is a 0, is equal to I, the current. So H5 R into, we got the 2 pi is equal to I, and the H5 is equal to I by 2 pi R, I by 2 pi R. Is H5 into A5 bar. H5 into A5 bar. What is the H5 here? I by 2 pi R into A5 bar. Now we got by using the Ampere circuit law, H bar due to the infinite long straight conductor, H5 is equal to I by 2 pi R. And similarly, the H bar due to the coaxial cable, H bar due to the cable means inside there is a, with the radius of A is one circle, and with the radius of B is another circle, and with the outermost circle is with the radius of C. H bar due to a coaxial cable. Consider a coaxial cable as shown in the figure. Its inner conductor is solid, which is a radius of A, and carrying direct current I. The outer conductor is in the form of concentric cylinder, which is inner radius of B, and outer radius is a C. Inner conductor is a solid with the radius of E. The cable is placed along the z-axis. This cable is placed along the z-axis. Here the z-axis only. Z-axis. The current I is uniformly distributed in the inner conductor, and while minus I is uniformly distributed in the outer conductor. See, current I is there in the inner conductor for outermost conductor. Or outer conductor, we can say. See the free body diagram or the cross-sectional view of circles with the radius of A, radius of B, and the radius of C. The first of all, assume the radius region 1. Region 1. With the inner radius R is less than the A. R is less than the A. Is a Gaussian surface. Consider a closed path having a radius A. Hence, it encloses only the part of conductor as shown in the figure. See the inner conductor, solid inner conductor. Now I am assuming the Gaussian surface inside the inner conductor A. The area of cross-section, enclosed in the is pi r square, circle area, pi r square. The total current flow is I, the positive I to the area. So the radius is pi a square. Radius of A, For radius A is a pi r square, and inner conductor is a pi a square because with the radius of A, and I dash is a ratio between of the two, I r square by I a square. Is r square into a square into I. That I is a positive here because inner conductor carrying the current is I plus I. So I dash is equal. The second case, now R H phi is equal to H bar is equal to H phi into A phi bar, and DL bar is R into D phi, the same thing. And according to the Ampere circuit law, H bar dot DL bar is equal to I. Now it is a current enclosed is I dash. What is I dash? We got R square by A square into I. Okay. So H phi R D phi is equal to R square by A square into I. H phi into R 2 pi R square A square into I is there. The I dash we got. Okay. Therefore the H phi is equal to R square by A square into I, and here R into 2 pi. Okay. Denominator is now I R by 2 pi A square. H phi is equal. Now the H bar is equal to, in the case 1, R is less than the A case, H phi is equal to H phi into A phi bar. What is the H phi? We got I R by 2 pi A square into A phi bar. H bar is equal. This is the first case. H bar is equal to I R by 2 pi A square into A phi bar. Okay, my dear students. Now in the second case, the R is in between of A and B. Now I am assuming the R. Okay. So consider a circular path which encloses the inner conductor carrying direct current I. This is a case of infinite long conductor along the z-axis. We know the H bar is equal to I by the 2 pi R into A phi bar. I by the 2 pi R into A phi bar. Means it looks like the same conductor is the current carrying conductor at the z-axis. Let us take like this, the z-axis, there is a current one circle with radius of A, another circle with the radius of B. And now I am assuming the Gaussian surface in between of the A and B. In between of the A and B, the Gaussian surface. Means the current carrying conductor is previously it is radius of inside the web. So I by the 2 pi R only. The current directly is getting I by the 2 pi R. It is not the I dash. Whenever it is in between of the B and the A. Got it, my difference? B and the A. Now the same, the region 3 within the outer conductor, the B and the C means B is greater than, B is less than, or and the less than C means R is greater than the B and R is less than the C. Now in this case, again it looks like there is a current carrying conductor, the Z axis, with the radius of B here, of C, radius of C. Assuming that the Gaussian surface is in between of B and C. B and C means inside there is a current, a positive current, and outside there is a negative current is there, minus I. Okay, madam. Minus I in the outer conductor the total current I is flowing through the cross section is pi C square minus B square. Okay, it's a minus I, the C square minus B square. So it is in between of the C and the B. The current is C square minus B square, pi R square actually, C square minus B square, while the closed path encloses the cross section is so one thing is a pi into C square minus B square, and the remaining is a pi into R square minus B square. As the total current is a ratio between of these two. I dash is equal to pi R square minus B square by the pi C square minus B square. The closed path is in between of P and C. First of all, you can subtract that is the ratio C square minus B square. Then after, we get the remaining part here, that is R square minus B square. Then you get the closed path, current passing through that. I dash is equal to pi into R square minus B square minus I is. So R square minus B square and C square minus B square into I. Here the minus is there, minus 2. The minus of this. Okay. Then to find the H bar, the total current I enclosed is I dash and I double dash. I dash is the current I because inside there is a current I. And I dash, I double dash is I current interclosed surface, that's R square minus B square is I into C square minus B square minus R square. B square get cancelled in the numerator C square minus R square and denominator C square minus B square. Okay. Because inside there is a current I is there and outermost the current is minus I. For minus I, you can consider it as I double dash is minus I into C square minus B square by C square minus B square. And the total current I is equal to I dash plus I double dash. So plus I is also you can add inside. Simplify this function C square minus R square by C square minus B square. Okay. According to the Ampere circuit law, H bar dot DL bar is equal to IN is equal to H5 D5 is H bar and DL bar is the same thing, R into D5 A5 bar. Okay. The total I enclosed is H bar dot DL bar is finally is H5 R D5 and I enclosed is I C square minus R square by C square minus B square. H5 into R 2 pi for every H5 into R 2 pi only on the right left hand side because it is the integral of H bar dot DL bar. The DL bar is always R into D5 A5 bar in this Ampere circuit law. H5 is R into D5. So H5 is equal to I by 2 pi R C square minus R square by B square. And H bar is equal to I by 2 by R C square minus R square by C square minus B square. Space is considered the outermost C, A is there and the B is there and the C is there. Now I am consuming the Gaussian surface outside. Inside there is a current I. Outside there is a minus. So plus I minus I is a 0. Plus I minus I is a 0. So the last case when the R is considered greater than the C, H bar dot DL bar is equal to 0. Okay. The first case H bar is equal to. The first case we got H bar is equal to R. See again. The first is in 0 to A. the H bar is proportional to 1 by R. You can write all these equations, then only you can understand. So the first case, H bar is equal to case 1. H bar is equal to I R by the case 1. And second case is similar to that of the long straight conductor, that is I by the 2 pi R K 5 bar. The second case. And the third case, what is the third case? We got H bar is equal to I by the pi R into C square minus R square by the C square minus B square. Third case. And in the fourth case, H bar is equal to the region I by, not I by, it is a 0. The value is a 0. H bar is inversely proportional to R, and H bar is proportional to R square, and here the inverse is there, and H bar is equal to 0. So it depends upon the R value, the graph is showing like this. In the range of 0 to A, the H bar is proportional to the R. See the first one, H bar, consider the remaining I by the 2 pi A is a constant, proportional to 1 by R, not 1 by R, it's directly R. So slowly it is increases as R is increases. Slowly it increases up to the A. Then H bar is inversely proportional. At the second case, H bar is inversely, consider this is a constant, proportional to 1 by R. So R is increases, H bar is decreases. So H bar is proportional to 1 by R only. So consider this totally is a constant. Still it is a decreases. In the third case also, to 1 by R1. Still it is a decreases. In the range 0 to A and A to B, when considered the Gaussian surface is inside the A. And second case, when the Gaussian surface is outside the in between of A and B, and the Gaussian surface is in between of B and C. The third case, and in the fourth case, the Gaussian surface is outermost of the circle. Is equal to 0. So goes to the 0 here. The first case, when the R is increases, gradually it is increases up to the A. And in the second case, inversely proportional means slowly it is decreases up to the B. And in the still there is a 1 by R only. Still it is a decreases goes to the 0. Got it, Madam? It's a very, very important.